This is a short introduction to nuclear chemistry, which plays a very important role in our world, not only for the energy it provides, but also all sorts of medical applications. There's actually a bit in our smoke alarms, not harmful at all. And it's used actually to kill bacteria in some of our food items. The message I would like to make at this point is nuclear chemistry. A lot of people have a gut reaction of it being dangerous. It does a lot of good in our world also. The key difference between nuclear reactions and regular chemical reactions are the particles in the atom that are involved. In a nuclear reaction, as the name kind of suggests, there are changes in the nucleus. Okay, and remember what's in the nucleus, right? Protons and neutrons. And because of that, often actually new elements are formed from other elements, which never ever happens in a regular chemical reaction. Regular chemical reaction only involves the valence electrons, that's outside the nucleus. You never change the element itself. That's where we get conservation of matter and balancing chemical reactions. You just don't see an element change into another one in a regular chemical reaction. Now, something I'll mention off and on in this is that I'm sure we've all heard of nuclear explosions, and you may be aware of the fact that we can get a tremendous amount of energy from a small nuclear reaction. All of that energy is due to what we call the binding energy, or the nuclear strong force that is inside a nucleus. So, of course, in the nucleus we have protons, right? And we have neutrons. I'm just putting a 0 for no charge, right? Okay, so if you think about it, you're packing particles that strongly repel each other into a tiny, condensed, extremely dense space. Why do these positively charged protons stay together? You'd think they'd want to blast apart from each other. Well, that is the nuclear strong force. Okay, it's the strongest force known to mankind, and that is the force that's released in radioactive reactions or nuclear reactions. There are some elements that spontaneously emit radioactivity, and they tend to be the heavier elements, and often only particular isotopes of an element. So every element beyond bismuth, Bi, which is atomic number 83, is somewhat unstable and is radioactive. So if you look at a periodic table, you'll notice where the mass usually is at the bottom of the periodic table square for each element, starting with bismuth, the mass, rather than being carried out to 2 or 3 or 4 decimal places, is a whole number. And of course, since these elements are heavy and they're radioactive, they're relatively unstable, that whole number mass is simply the mass of the most stable isotope, which is radioactive. So you can see now, if you look at this graph, that as we increase the number of protons, as the atomic number increases, it's more and more likely that a substance will be radioactive. The stable ratio of neutrons to protons follows this kind of yellow-green line. So you can see as the number of protons increases, you need progressively a higher percentage of neutrons in order to stabilize that element. That makes sense, right? If you're putting in more protons, you're increasing that incredibly strong repulsion force between protons. So if you add on a percentage basis more and more neutrons, you're kind of diluting that repulsion. So up to about atomic number 20, there is about a 1-to-1 ratio of neutrons to protons, and that is the stable ratio. Okay, you can figure that out for yourself. If you were given mass numbers and atomic numbers, there's about an equal number of protons and neutrons. Beyond atomic number 20, it requires progressively more and more and more neutrons to keep the element stable. The three most common types of nuclear radiation, I'm not sure why that is there, are alpha, beta, and gamma decay. There are more types of decay, which I'll introduce briefly, but these are the most common, the ones that you should be most familiar with. An alpha particle, sometimes shown with this alpha symbol, and if we were to put, remember that the upper left is the mass of something, and the lower left is the number of protons. Sometimes it's shown with this alpha symbol, sometimes it is shown as a helium nucleus. Why, you might ask? Because a helium nucleus literally has a mass of 4. Okay, if you look at a helium nucleus, it has 2 protons and 2 neutrons, so it has a mass of 4. And it has 2 protons. Now, sometimes you'll see, since it's only the nucleus, an alpha particle does have a charge of +2. So sometimes you'll see that charge, but even if it's not shown, it's there. Beta particle is literally an electron. So you might ask, if it's an electron, why are we calling it a beta particle? Because of where it originates from. It originates from the nucleus, which is very strange. But as you'll see later, it starts from a neutron in the nucleus, and that neutron breaks apart into a proton and an electron, and that electron is what we call a beta particle. So it's its origin that makes it into a beta particle. And then finally, gamma rays, pure energy. Okay, there's not really a particle. Some people can call light a particle, but it's not a particle with mass. It's the form of energy that's let off in nuclear reactions, and most nuclear reactions do let off quite a bit of energy, so it is in the form of gamma rays. This is just a picture. There's nothing new here, okay? Just kind of a quick summary to let you know what the 3 most common types of decay are. All right, just a little piece of information you should be aware of, the penetrating ability and therefore the danger to us of these 3 common types of nuclear radiation. Alpha particles are the heaviest, but they're the least dangerous, okay? And beta particles, being a little bit lighter, tend to have faster speed, and their ability to penetrate and their danger is a bit higher. So if you're being attacked by alpha particles, you can simply hold up a piece of paper and bounce them off of that. You need a thin layer of lead. If they're beta particles, if they're gamma rays, those are the really dangerous ones, okay? That's when you need a big block of lead to protect yourself. All right, some of the other nuclear particles, which we'll mention briefly, won't spend quite as much time on. Neutrons are often used to bombard an unstable nucleus and start a nuclear reaction. Nuclear energy plants will often use a neutron to start the reaction fission used in nuclear energy plants. But just so you're aware of the symbol, okay, and little n for neutron, obviously. There are no protons, that's why that's 0, and neutrons have a mass of 1 AMU. Positron, okay, it is the antimatter, which we'll talk about a little bit in a couple slides, but it's basically has the same properties of an electron, except its charge is +1 rather than -1, okay? And a proton, you're familiar with that from doing the acid-base segment, right? So a proton can be shown as hydrogen ion, which is what it is. In nuclear reactions, it's often shown as this. You'll notice that a lot of times in nuclear chemistry, they don't actually show the charge in the upper right like we do with normal chemical reactions. So I just want you to be aware of that. All right, one of the things you need to be able to do to apply this knowledge about the different types of nuclear radiation is to balance a nuclear equation. There are tons of different ones, and they're really easy to balance. All you have to do is make sure that you conserve the total mass involved and the total number of protons involved. So the mass, again, is the number in the upper left, and you want to make sure that that total mass of all the particles that are reactants on the left side of the arrow equal the total mass of all the particles on the product side of a nuclear reaction, okay? Conservation of mass. You want to make sure that you also conserve the number of protons on both sides, right? Okay, so it's pretty simple. So if you're given a reaction and let's say they leave out one of the products, you should be able to figure it out with simple math. Here's one for you to try, and using what I just said, and I'm not going to give the answer here because it's a go formative, but this is the typical type of problem you're likely to see multiple choice on an exam, and it's pretty simple. All right, I'm going to go over each of the types of decay with just a little bit more detail. The alpha particle, again, is usually shown in symbols as the helium nucleus. It is made up of 2 protons and 2 neutrons, and what happens is if you have an unstable nuclei, I think we've all heard uranium is a naturally occurring radioactive element deep in our earth, and it will spontaneously emit an alpha particle from its nucleus, and that's its effort to become more stable. It's kicking out some of the protons and trying to stabilize. And so how you might write this in symbols is uranium 238. And uranium has an atomic number of 92. And it emits an alpha particle. And you could even without being told, you could figure out what it makes by simply doing some math. So we have 92 protons on the reactant side. We need 92 also on the product side. So we know that the other element formed has an atomic number, or 90 protons. And if you look at your periodic table, that is thorium. And the mass of this isotope of thorium would be 238 minus 4, which is 234. So here's another example. This would be a typical problem you might be asked. Polonium decays by alpha emission. Write out the balanced nuclear equation for it. So again, you've got to have memorized what an alpha particle is. You have to look in your periodic table to find the atomic number of polonium, and it happens to be 84. Again, if it's alpha decay, the alpha particle is a product, and then just simply do your math. 84 minus 2 is 82. 212 minus 4 is 208. And then you look on the periodic table and you discover that is lead. Okay. We'll go through the same process for beta decay. Carbon-14, an isotope of carbon that is present only in the upper atmosphere, a fascinating isotope. It's used for doing aging of substances that used to once be alive. So a lot of old trees or documents that are made from paper from old trees can be dated with carbon-14 dating. Anyway, so writing this in equation form, carbon-14, we know the atomic number of carbon is 6. We were told it undergoes beta decay, so one of the products has to be the beta particle. I tend to write, and of course we assume electrons have a mass of 0, even though we know they have a minuscule mass. And it doesn't have a proton. They account for the -1 charge down in the lower left, which is a little weird, but it helps you do your math for the protons. And then you can figure out what's left over, right? Let's see, so in this case, the mass would be the same, right? And it's weird, but in beta decay, you actually gain a proton. So, right, 7 minus 1 is 6. And that's because if you look at what I showed you that beta decay is, it starts with a neutron, which decays into a proton and electron. And so you actually form an extra proton. And so then you look at what atomic number 7 is. It is nitrogen. And here's just another example. So this is just kind of remind you if you want to jot it down or something. That's how we would show formation of a beta particle. And this is the reaction we just did on the last page. And here's another one. So if you are told that something decays by beta decay, beta emission, you simply want to make sure that you increase the number of protons or the atomic number by 1, and then the mass stays the same. Here is one for you to try, okay? Which I'm not going to work out here again because people in my class will need to do it on Go Formative. Now this is just kind of cool. Antimatter is real. You've probably heard of it, but you may not know exactly what it is. It's basically, there's a theory that everything in our universe, all types of matter, have another type of matter that's exactly opposite of them. So, for example, with charged particles, like a proton and electron, there should be a particle in the universe that has the same mass, for example, but a different charge. Okay, so for example, protons with a negative charge are called antiprotons, and they have been confirmed to exist. Electrons with a positive charge are called positrons. Okay, so again, they have the same mass and some other properties, but the charge is what distinguishes them. So these opposite types of matter are called antimatter, and it is true that if antimatter comes close to one another, they do annihilate each other. So you lose each particle and you get quite a bit of energy in the form of gamma ray emitted from that encounter. So let's talk about radioactivity that involves positron emission. So the symbol for a positron is very similar to that we use for a beta particle. So mass of 0, and of course now we have the +1 charge instead of -1. And remember that, just for comparison here, remember that beta particle came from a neutron starting in the nucleus, which decays into a beta particle and a proton. Okay, so for comparison, a positron starts from a proton in the nucleus, which decays into a positron and a neutron. And I did that wrong, didn't I? That should be 1. Okay. Okay. So, for example, carbon-11 can undergo positron emission. So if we were to write a symbol for that, the 11 represents the mass. We know the atomic number for carbon is 6. A positron, the symbol for it is like the beta particle, right? But now we put +1 here instead of -1. So to do our simple math, we know that it creates atomic number, 5 + 1 is 6, right? And so what element is atomic number 5? It happens to be boron. Not good, we have 2 B's here. And of course the mass stays the same, just like it does with beta decay. So all of this can get confusing, I know. So honestly, I'm just going to come out and tell you on my exam, I'm just going to go over alpha, beta, and gamma. But on your final exam, you may see some of these other more obscure types. All right, so again, this is how you form a positron. It starts with a proton in the nucleus, decaying to a neutron and a positron particle. This is the reaction we just did on the previous slide. Here's another example for you. All right, the last kind of obscure nuclear reaction is called electron capture. Okay, that is just like it sounds. You have an unstable nucleus that just swallows up another electron. And of course, since these are nuclear reactions, the electron is going to go into the nucleus. So you might be able to guess at this point, what do you think an electron will combine with? Okay, so if we have an electron and it goes in the nucleus and combines with a proton, what do we make? A neutron. Okay, so you end up with an extra neutron. So this is kind of the reverse of beta decay. Because remember that beta decay kind of goes in the opposite direction. You start with an existing neutron and it breaks apart into a proton and electron. And a couple of equations written out for you. Here's just showing the formation or what happens when you get electron capture. So there's the electron being captured combined to the proton in the nucleus. So it basically is converting a proton in the nucleus to a neutron. And of course, that's making it more stable. It's reducing the proton-proton repulsion. Almost done. Typically in nuclear decay, there are several elements, as I said, uranium-238 being one of them in our world that naturally, spontaneously decays. And we use graphs like this to show. And so I might ask you to interpret a graph like this as a multiple choice question. So I want you to be able to understand how to use them. So let's start with an unstable nucleus. Let's just start here, okay? And I want you to notice what is on the x-axis and y-axis. So we have number of neutrons in the nucleus on the y-axis and protons on the x-axis, sorry. So beta decay, we've got to remember what is a beta particle, right? That means we're starting with a neutron in the nucleus and it is breaking apart to form a beta particle and a proton. All right, so you're decreasing the number of neutrons by 1, okay, so that if you're starting here, you go down, the number of neutrons is decreasing, it's going down by 1, right? And you're gaining another proton. So we're gaining another proton. Okay, so hopefully now you can kind of interpret how these radioactive decay graphs work. So beta decay is always going to go diagonally from the upper left to the lower right. So that's probably something you could write down to remember it, right? And let's look at alpha decay. Let's start here for alpha decay, and then let's remember what alpha decay is, right? So when something emits an alpha particle, it decreases in mass by 4, right? And what is that mass made up of? It loses 2 protons, right? Because an alpha particle has 2 protons in it, and it also loses 2 neutrons. That's what an alpha particle is made up of, 2 protons per 2 neutrons. So if you're doing alpha decay, you want to go down by 2 in your neutrons, right? And also decrease by 2 in your protons. So alpha decay is going to start in the upper right and go diagonally to the lower left. So you definitely want to get these 2 processes, be able to show them and interpret them on a graph. And that is it for this introduction to nuclear chemistry.